So wonderful. Good morning, dear LinkedIn community, Composites launch members, UCIA members, ECA signatories. We are here at another fantastic and spectacular project that we will introduce to you, and that is the EOLIAN project. We are going all in the circularity, recycling, sustainability matter one more time. Yeah, and I would like to introduce you to shortly give you an overview about our guests today. So we got Giulia Di Dio from ProPlast.
Good morning.
Morning, Giulia. She is from Italy, near Torino. Then we got Cristina Monteserin from Spain.
Good morning.
The Basque Country. Andrea Minigier from AP Polymers, Italy, in the northeast, Trieste.
Good morning.
We got Marco Longana, and he's also from Italy, from Milano. And Marco will be helping us out now because, as you may have noted, Roberto is not here in the live stream right now because of some commitments they came up on very short notice. So thank you, Marco, for giving us the introduction on this EOLIAN project before we dive directly into the presentations. Then we got Daniel Paul from London, UK, Brunel Composites.
Hello, good morning.
Dr. Fotini Petrakali from Greece.
Hello, good morning.
Athens. Claudia Vasquez Norrento Techin Power from Spain, Galicia. And then we got Zeynep Korkmaz from Istanbul, Turkey. So we are a complete round of experts here. And I would like to start then with Marco. And Marco, yeah, please give us an idea about the EOLIAN project. How did it evolve? How did it come? What was the idea behind it?
The idea behind it was substantially to substitute traditional constituent materials of wind turbine blade, which are glass fiber and an epoxy matrix, with more sustainable, more circular material, namely basalt fibers and vitrimer matrices, to substantially have a wind turbine blade that would be repairable, recyclable. We also decided, thanks to the partner in Techniker, to add sensing capability to the blade, so to detect ice formation and possible damages, and basically create wind blades that would be reliable and sustainable. The project substantially works on addressing a fundamental problem of current vitrimer matrix composite, which is the relatively low TG and the high difficulty in adapting them to available manufacturing technique or used manufacturing technique for wind turbine blade, namely infusion. So we have two partners that are looking at formulating new vitrimer with ITG and let's say the capability, the possibility to be infused, so with the low viscosity, at least at the beginning, during the cross-linking, during the manufacturing phase. And then we have IP Solution, who's IP Polymers, sorry, Andrea, who's taking care of the upscaling of the production of this vitrimer. We have us in Polimi. We are taking care of material characterization and end-of-life solution. We have partner in Brunel and Entelea who are looking at the modeling of these molecules, these vitrimeric polymers. We have Iris, who's watching after all of us, and in terms of LCA, LCC, and in terms of safe and sustainable by design. Finally, we have Norvento, who is a wind blade manufacturer and operator, who will take care of the realization of the demonstrator. I think that one of the strong points of this project is the realization of a full-scale wind turbine blade demonstrator made with basalt fiber and the vitrimer matrices that we are developing in our project. And finally, we have Zorlu Energy, who is substantially a provider of energy and services, who gives us an idea and an overview on a more commercial and applicational sort of aspect of the project. This, I guess, pretty much.
Okay, that's fantastic that you already, in some detail, introduced us the panelists. But Marco, let me come back shortly. Why should people care about this EOLIAN project? Why is it so important that you decided to make this project?
Because there is an image that wherever you go and talk about composite, you see, and is that famous image, I think it's from Wyoming landfill, where you see hundreds, you smile because you know it, you've seen it probably everywhere. Yes. There are hundreds of wind blades that are being buried in a landfill, and that substantially it's a perfectly good material that is going substantially to waste. Why? Because the matrix that we are using, the cross-link matrix that we are using, the thermoset matrix that we are using to produce current wind blade, is very complex to recycle and to recycle in high value, and also is very complex and difficult to repair. The idea is that if we manage to shift from thermoset to vitrimers, who are a kind of thermoset, but they also behave like a thermoplastic, we have the possibility of repair more easily the structure, and we have the possibility of devise new end-of-life strategy to bring back high-value composite material into the supply chain, into the manufacturing chain, and this is basically the attempt of the project.
Marco, then my final question for our viewers that are maybe not so iterate on how such projects like EOLIAN work. Can you walk us through how is the process of starting a project like EOLIAN? I believe it is funded by the Horizon European Commission program. How do you start this? How do you process this? How often do you meet? Are there any milestones? Yeah.
Okay. So how does it start? It usually starts with, I would say, a couple of friends from two different organizations who have an idea. And probably in our case was, it would be cool to use to do vitrimer matrix composites. And we thought, okay, where we could apply them. And we saw the wind sector as one potential application of these matrices. From that, you sort of expand the circle of partner till you reach the point where you think you are covering the whole supply chain somehow, but let's call it the knowledge chain, okay? We know in Politecnico what we are good at, and we know what we are weak at. So we go and we find a partner that might compensate our weakness with its strength. And substantially, you end up creating a consortium. Once you have a consortium that is built around an idea and a concept, there is probably the most painful phase, which is the writing of the actual bid. And in the bid, you end up defining, let's say, an R&D process. You know where you're starting, you know where you want to get. You define the intermediate steps. You allocate tasks or work packages and tasks to the different partners that they need to work in close collaboration. And then you submit your bid to the European Union, and you keep your fingers crossed for a certain amount of time till the project gets founded, and then the project runs substantially on. There is a kickoff meeting where we know already what are our role, but we discuss more in detail what will be done. And then we regularly meet in person every 6 months, online every month, period where there is a strong need of collaborate on a daily basis, almost via mail, via Teams, via phone, via whatever mean. There is, especially for this project, where we are the user of a material that is, or a matrix at least, that has been developed by another partner. There is a lot of exchange of material information, visits, a sharing of knowledge and expertise and capabilities. So maybe somebody comes and gets trained on doing an infusion, somebody goes and gets trained on how to operate the sensors that Techniker is implementing in the wind turbine blade, and so on. We of course have some deliverables that we need to upload to the European Union portal. Some of them are confidential, because the idea is to be able also to generate IP and knowledge and exploitable results, not only on a scientific point of view, but also on a commercial point of view. Some other deliverables are public. There are activities of dissemination, and so on. Finally, the project closes, and our project will close to the realization of a large-scale demonstrator that hopefully is the sum of all the research, R&D, and intellectual work and the practical work as well that goes on during a project.
Okay, cool. So, dear community, now you know how these projects work, and if you have ideas, I'm sure you can apply on them during, if it's in Composites with the UCIA, or approach the Horizon Europe. So thank you so much, Marco. I will come back to you later on. Yeah, after a very short break, now we will be going into the panelists today, and starting with Giulia Di Dio from ProPlast, just after this short break. So, Giulia, welcome to our live stream today.
Thank you.
Coming from Italy. Is it also so hot in Italy like it's in Germany right now?
It's
hot, yeah.
So hot, yes.
Yeah, but today, this night, we had nice rain, so it's okay right now. You had also rain. That's cool.
Yeah.
Okay, Giulia, then I would say how this works, dear community, is I have panelists here. We are nine people, including me as a host, and we will be, or the panelists will be introducing you with a prepared presentation, their part, their role in this project. And before we start with Giulia, dear community, I see already some comments over there, like from Attila Öztürk, who has wished us a fruitful event. Thank you so much, Attila, on this one. And anyone else, I'm seeing quite a few people are watching us. Please write down in the comments from where are you tuning in right now, because we want to reach or measure the reach of our live stream here. We would like to get to know to you guys. Please connect among each other. Also, this will be soon a audio podcast, so I'm greeting our audio podcast app listeners if you listen to this the first time on the podcast. So if you want to watch the presentation, you have the option to go on LinkedIn on my profile, or you can also watch this on YouTube podcast and you can watch the presentations over there. Yeah, Julia, without further ado, then I would say let's start with your presentation. Let me find it. Okay, I think it's this one. The stage is yours.
Thank you very much. So good morning, everyone. I am Giulia Didier. I'm a researcher at Proplast in the Materials Engineering Department. And I am a part of the Proplast team that works in the technical activity within the EOLIAN project. Oops, okay. So just a few information about Proplast. So Proplast is a technological center that is specialized in research and development of polymers and composite materials. Proplast activities range from technical skill development, such as training activities, profile selection, to participation in collaborative research projects at European, national, and regional levels. It also focuses on environmental topics. In fact, it proposed sustainability reporting and life cycle assessment studies. Also, Proplast is recognized as a European-level innovation cluster. In fact, it promotes networking and collaboration by organizing thematic events and workshops. Regarding the EOLIAN project, the role of Proplast is the coordination, is to coordinate the project and to perform technical activities in vitrimer formulation, testing, and evaluation of recyclability. As has already been said, the general object of the EOLIAN project is to try to substitute the current wind blades material with bio-based, repairable, and recyclable vitrimer composites in order to try to improve the sustainability of wind blades and to extend their service life. The blades will be integrated with recyclable sensors and heating actuators, and the overall project will be supported by advanced multi-scale modeling and life cycle assessment analysis. Okay. Regarding the Proplast activities, it mainly focuses on the development of advanced material based on dynamic covalent bonds. These dynamic bonds are the main characteristic of vitrimers. Vitrimers are this class of materials that exhibit intermediate properties between thermoset and thermoplastic. In particular, they can show the thermoset mechanical properties while remaining reprocessable like thermoplastic. So among the wide possible chemical strategy to try to produce a vitrimer, we chose to focus on functionalizing the hardener component of this kind of resins by inserting dynamic covalent bonds. And we chose two types of chemistries, the imine and the disulfide. And basically, we synthesize these hardeners that will contain the dynamic bonds, and this bond is the actor that will promote the recyclability and the repairability behavior of these vitrimeric systems. So regarding our activity, we were able to synthesize several and different hardeners that showed different properties, and to produce the corresponding vitrimers also that, as you can see, they show different colors and also flexibility and different properties. So the selection of these hardener depends mainly on two parameters, the TG values, and of course the processability, that is strictly related to viscosity of the vitrimeric system, that is very important since the manufacturing of the composite panels is made by vacuum infusion, which is strictly related to a good viscosity parameter. So to improve this processability, at one point the diluents were incorporated into both the hardener and the epoxy resin components. However, these diluents often reduce these TG values. So one of the main core of this research study was the formulation optimization, and to find a trade-off between the vitrimer processability and the thermal performance that must be in accordance with the requirements of the project. So at last, once we were able to produce our vitrimeric resin, we proceed by manufacture the composite panels. In the case of Proplast, we were able to produce this heated metal plate that was specifically designed internally for this application. And then, thanks to this heated plate, we were able to produce these composite panels by using basal fibers and our vitrimeric matrix. We showed some images of this vacuum infusion procedure. And so the objective was to produce these panels that will compose will be the main structural component of the wing blade and will be repairable and recyclable. So thank you everyone for the attention.
So that was fast and sweet on the spot. Thank you so much, Julia. Yeah, we will then move to Christina. Christina, let me see. I have quite a number of people there. Yeah, and I'll come back to you, Julia, later on. Okay. So Christina, she is from Techniker and from the Basque Country. So we got a couple of Italians, Spanish, Greece. So the south of Europe is very much represented today.
Yes.
Good. Also hot in your place right now?
Yes.
In the Basque Country? Also very hot.
Very hot.
Okay, but we need to make a more sustainable world, and you guys, you help in getting more sustainable technologies there so that our climate protection goes further. Christina, so you have prepared also a presentation for us, and
Yes.
I would say, let's go. The show is yours.
Okay. You can see, because I can see the presentation. Yes, now yes. Okay. Thank you and good morning, everyone. I'm Cristina Monteserin from Techniker, and before introducing our work in EOLIAN, let me briefly present the company. Techniker is a non-profit research and technology center with more than 45 years of experience in applied research and innovation. We support industrial competitiveness by developing high-value solutions in three main areas: advanced manufacturing, surface and materials technologies, and digital technologies. Our mission is to help companies to solve technological challenges by transferring knowledge and innovation and contributing to a more sustainable and competitive society. We are located in the Basque Country in the north of Spain. So within EOLIAN, Techniker works on two research lines. The first one, advanced materials with dynamic covalent bonds, and the second one, the integration of sensor and actuators for structural monitoring and maintenance. So starting from the first of the research line, and as Proplast has already mentioned and introduced, and to provide some context, the wine blade industry is looking for more sustainable and recyclable materials without compromising performance. This is increasing interest in alternatives to traditional composite. One promising option is the use of covalent adaptable networks, which combine the strength of thermoset with the reprocessability and recyclability of the thermoplastics. Among them, the vitrimers are especially attractive because their dynamic bonds allow them to respond to external stimuli, such as temperature, offering valuable functionalities such as memory behavior, reprocessability, recyclability, and self-healing capabilities. At Techniker, our contribution to EOLIAN focuses on the developing sustainable epoxy vitrimer materials for future wind turbine blades. To do this, we create dynamic hardeners from vanillin, a bio-based raw material, and diamines. These dynamic bonds make the material recyclable, repairable, and reusable. At the same time, we increase the renewable content by replacing conventional fossil-based epoxy resins with epoxidized vegetable oils. This combination allows us to develop a bio-based vitrimer material that offers the performance of conventional thermoset together with repair, reuse, and recycling capabilities. We can develop materials with a bio-based content exceeding 60%. Their mechanical and thermal performance has been evaluated against the requirements of wind turbine blade applications and can be further tailored through formulation adjustments. In addition, we have proved that the dynamic network imparts advanced functionalities, including the repairability, the reprocessability, and the recyclability, thereby enhancing both materials durability and circularity. However, good material performance is only part of the challenge. For industrial use, the materials must also be compatible with current wind blade manufacturing processes, especially resin infusion. So this means that properties such as viscosity, resin flow, curing behavior, and processing time must be carefully controlled. The challenge is to maintain the recyclable nature of the vitrimer while ensuring efficient large-scale manufacturing. For this reason, as Proplas mentioned, other dynamic chemistries such as disulfide-based systems are also being explored to further optimize the material properties and processing. So our main objectives within EOLIAN are to develop these sustainable epoxy resins with bio-based content and free of bisphenol A to develop these materials for wind turbine blade that meet processability and performance requirements while incorporating these dynamic bonds, enable repair, reshaping, and recycling, and support the development of recycling solutions for next generation of wind turbine blades and contribute to a more circular wind energy sector. As expected impact, these materials have the potential to reduce composite waste, open new routes for repair and recycling, improve the circularity of wind turbine blades, and contribute to a more sustainable wind energy industry. Then moving to the second research line, we focus on smart monitoring technologies and maintenance methods. Wind turbine blades work in very harsh conditions. They are exposed to rain, erosion, temperature change, and ice. Over time, this can cause damage and increase maintenance cost. So the goal is to turn traditional blades into smart structures that can monitor their condition in real time and react when needed. To do this, we focus on three main points: integrating sensor and actuators into a composite, so the monitoring system becomes part of the structure, testing and validation this sensor to ensure they work reliably in real conditions, and developing control and optimization algorithms. So, the concept developed within the EOLIAN project is to create a multifunctional composite structure by integrating both sensing and actuation capabilities directly into the wind turbine blade using in-mold electronic technologies. A hybrid multi-layer system is proposed where the sensor and actuators are integrated into the wind turbine blade using this in-mold electronics. The system includes an ice sensor placed near the surface to detect the ice, and then a heater to remove it. Both are made using printed electronics on fiber fabrics, allowing easy integration into the composite with a minimal impact on its mechanical properties. In this slide, we present the electrochemical impedance spectroscopy-based ice sensor developed within the project. By applying small electrical signals at different frequencies, the sensor obtains an electrical fingerprint of the material on the blade surface. Since water and ice have different electrical properties, they generate different impedance response, allowing the sensor to detect ice formation. Here, in this slide, we show the functional validation of the complete de-icing system, integrating sensing and actuation. When ice accumulates on the composite surface, the sensor detects its presence and automatically switches on the heater. Once the ice has melted and the surface becomes ice-free again, the system detects this condition and switches the heater off. The sequence present here shows the different stages of the process. The graphs show the thermal and electrical response of the system during the validation test. The temperature profile reflects the different test stages. Once the heater was switched on, the temperature increased until the ice is melt, and then decrease again after automatic heater deactivation. The electrical measurement also confirmed that the correct operation of the heater and show the expected increase in resistance with temperature. These results demonstrate the successful operation of the complete sensing and actuation and validate the autonomous ice detection and removal concept developed within the project. Just to conclude, we aim to integrate sensing and heating functionalities directly into the composite demonstrator, enabling the structure not only to detect ice formation, but also to react autonomously through embedded electronics. The expected impact in the demonstration of multifunctional composites with integrated electronics that are capable of reducing performance losses caused by icing, lowering maintenance cost, and extended blade lifetime. More importantly, this work lays the foundation for scalable and adaptable smart blade technologies that could be implemented in future wind turbines, improving their reliability, efficiency, and sustainability. And this is all for my side. Thank you very much.
So thank you, Christina. It was very, very interesting. You sparked my interest in one of your slides where you said, okay, we have to also observe that the industries have existing processes and that it needs to be worked on industrial processes. So that sparked my interest, and I will ask you guys in a panel, why are then industries so slow in adopting new modern processes? Yeah? A bit provocative, maybe, this question, but I'd like to hear your opinions on this one. Thanks for this inspiration. Okay, then we will continue with Andrea. So Andrea is here, and I will come back to Christina later on. Yeah, Andrea, you are at IAP Polymers, Italy, Trieste, the Northeast. Welcome to our show, and I would say we start directly also with your presentation, which I will find, and I think it is this one here.
Yes, thank you so much for the introduction. And good morning, everyone. My name is Andrea Miniger. My background is chemical engineering, and I am one of the co-founders of AP Polymers. We founded the company in 2013. We are based in the Area Science Park of Trieste in the extreme northeast of Italy. AP Polymers is an SME fully dedicated to industrial R&D, especially on the development of new bio-based polymers and chemical building blocks and formulation. Our expertise is a blend of two pillars: organic chemistry from one side and polymer science from the other one. Every day we perform, let's say, two main types of activities. One is to design and develop new bio-based polymers, also benchmarking them against commercial products. The second is we assess the usability, the industrial usability of new bio-based products or developmental products, for example, new grades of lignin or fraction from biorefinery operations. So we operate at the lab scale up to TRL of 4 to 5. We don't have a production and commercialization because our products are knowledge and recipes. Our main application sectors are in polyurethanes, so rigid foams, flexible foams, the huge area of case, so coatings, adhesives, sealants, and elastomers, but also in fiber-reinforced composites, This is why we are part of the EOLIAN consortium. And a few years ago, we started to work also a little bit on thermoplastics, especially on bio-based ones. And we every day work with the industry in three main ways. So consulting works, laboratory services, and of course, R&D funded projects. Our role in EOLIAN, first is the formal role is WP5 technical leader. From the practical point of view, we connect the development of vitrimers in WP2. So Julia and Christina have already described the developments of new vitrimers with the production of demonstrators, which is made in WP5. And as already mentioned, there is a real scale wind turbine blade, 12 meter long. This is the real challenge, operational challenge of the project, and then smaller 1 meter parts. So the key activities in WP5 are the scale-up production of the selected vitrimers, and we are now in. We have just selected the more promising, the more performing one, and we are preparing to upscale the production. The second activity, which was already done by Norvento, is the design and manufacturing. Is the design of the vitrimer-based composite wind blade. The manufacturing will be made next year. And then also next year, the validation of operability and durability assessment and the use of recycled vitrimers to produce a section of wind turbine blade. So the recyclability concept that was mentioned earlier by Marco. The challenges that we have been facing connecting the vitrimer development and the expected production of the wind turbine blade is to satisfy a wide range of process and product requirements, which sometimes are very conflicting. For example, we have a viscosity, which must be suitable for the infusion process, which is used by Norvento. Also the pot life of the formulation of the resin, but also the stability over time of the two separate components. The glass transition temperature, tensile and flexural properties, but also cost, also the environmental aspects, so bio-based content, low environmental footprint, health and safety. So I look into the raw materials that should have a safety data sheet as clean as possible, and also to the process conditions, so avoiding, for example, harmful solvents or replacing them with less harmful one, and of course, without losing the vitrimeric properties. An example of conflicts here is, for example, viscosity. We need to lower the viscosity. We add more diluents, as Julia mentioned, but this way you also risk to lower too much the mechanical properties and also the glass transition and temperature. So at the end, the complexity is to find out a balance between all the properties and optimize as much as possible. And this is my presentation.
Okay, Andrea, thank you so much. That was fast. Also from your side, I got a new question that raised in my head. This is the cost on bio-based content that you have mentioned. So we will discuss that also later on, and I will come back to you later on. Okay, then next in line is Marco. We had Marco in the introduction, so now it's time for Marco to introduce his role in this EOLIAN project.
So yes, I think I'm having a little bit of delay on my line. If you don't mind, I'll start talking. I'm Marco Longana. I'm from Politecnico di Milano, the Department of Chemistry, Chemical Engineering, and Material Engineering. I'm working on the EOLIAN project together with my colleague, Professor Claudia Marano, and we have 2 PhD students that we were able to hire on this project to help us with the experimental work. So what are we doing within the EOLIAN project? Substantially, we are characterizing the material that we are developing, and in particular the composite material that comes from the infusion of basalt fiber with the vitrimer that IPE, Techniker, and also Proplast are developing. We're working on the assessment of the vitrimeric behavior. As has been explained before, vitrimer, they have the molecular structure of a thermoset, but somehow the behavior, the processing behavior of a thermoplastic. So we are trying to do this, and we are trying to characterize this behavior, and we are devising and working on end-of-life strategies. So first of all, we are, unfortunately, this is a video, but it's not running. We are basically working on infusion trials on, of course, you can see from the image on a small scale of the vitrimer matrices that have been developed by our partner. Key factor here are the viscosity and the gel time. We need to be as close as possible to already existing matrix systems in the industry if we want to have the vitrimer to be uptaken as a possible alternative to them. So we are doing all our work on this, plus we are looking at some parameter which might be exotherm during the infusion and curing process, and all the little difficulties that the day-to-day industry needs to tackle when producing a composite structure, especially a large one as a wind turbine blade might be. In terms of characterization, we are conducting, after we, of course, produce our panel, all those standard sort of characterization exercise that are needed to be able to design a blade with a new material. So the typical tensile, flexural test to get stiffness and strength of our material. And most importantly, we are working on the assessment of the repairability of this vitrimer matrix composite. A standard, of course, it doesn't exist yet. One of the targets would be at least to propose repeatable and coded standardized way to assess the repairability of a vitrimer matrix composite. We're doing this using a double cantilever beam test, which substantially allows a crack to propagate in mode 1. In this way, we are substantially damaging only the matrix, and we are not compromising the fiber integrity. Once we have a first evaluation of the mode 1 toughness of our material, we proceed with the repair of the material by simply applying heat and pressure. Of course, we need to be able to identify the correct temperature to apply to our material to be able to repair it. And then we conduct a second DCB test, and from the comparison of the fracture toughness in mode 1 that comes out from the second DCB test, we are able to evaluate or provide healing efficiency for our material. Second big field where we are working on is basically the end-of-life management strategies. Typically, thermoset matrix composite are recycled in a two-step phase. A first phase of fiber reclamation, where we try to degrade the matrix and extract the fiber. Of course, in this proceeding in this way, the value of the fiber of the matrix is lost. Vitrimer are able to be simply reshaped So we might think about taking a structure that has a certain curvature, impose, once again, heat and pressure to the structure and obtain a flat panel. This flat panel, it's already a composite panel. It has already a certain fiber orientation and distribution, fiber volume fraction, and this panel can be used to machine out new parts that might have a second life. So rather than a recycling, if you want, is a reuse approach. Secondly, again, with this concept of trying not to separate the two phases, fiber and matrix, we are trying to develop a mechanical recycling strategy. So we start from the layer structure of the composite. We are developing a technique to delayer the composite without compromising the fiber, or minimizing at least the fiber breakage. Once we obtain the individual ply, we are able then to simply reassemble them and lay up in a new structure and obtain substantially a recycled vitrimer matrix composite. Again, there are several challenges, a lot of intermediate steps to develop, but we are working hard on it, and the vitrimeric nature of the matrix allows this recycling process, mechanical recycling process at low cost, without going too much back into the value chain of the composite itself. So this is a very, very brief overview of what we are doing here in Polimi with the composite. Thank you very much for the attention. I'm sorry, I cannot hear you.
So thank you, Marco, for your explanation and also your introduction to the matter. Now we will continue to Daniel Paul. So if we are going from the south more to the west of Europe.
Yep.
And Daniel, you have a presentation as well, which
Yep.
is this one.
Yes.
And I leave the stage to you.
Yep. Thank you, Ulrich. And hello, everyone. So we'll just take a shift from the experimental part to the modeling part right now, which we have done under EOLIAN. So about myself, I am Daniel Paul. I am a research fellow at Brunel Composites Center. And this is the work that I'm presenting on the modeling work that we have done under the EOLIAN project together with Brunel Composites Center and Intelia Limited. So a little bit about Brunel Composites Center. So we are an innovation center established as a joint collaboration of Brunel University and TWI Limited. So we sit at the intersection of academia and industry. So we work both very closely with research projects as well as a lot of industry-oriented projects as well. So what do? We do everything composites, innovation in composites. So that can start from manufacturing and testing methods in composites, or it could involve modeling and design of composites, the structural integrity and structural health monitoring, sensors, and recently we have been using ML-based methods as well in composite materials to progress innovation in composites. And also we work quite a bit on sustainability of composites as well. So what we do in this project, so our contribution to EOLIAN is mainly in the modeling side of things. So as I said, Brunel Composites Center together with Intelia are taking care of this work package. And the aim of this task was to develop a comprehensive framework to predict the properties of vitrimers and composites by using first principles, by minimizing the necessity for performing experiments, and to try to develop a modeling framework which can be used to predict the properties from scratch. So this is kind of like the workflow that we have followed. So we began at very low atomistic molecular scales, and then we move on to the higher level experimental scales, composite scales such as micro, meso, and macro scales. So our aim was to create a framework throughout these scales to get a prediction engine up and running. So I'll very briefly go through what we have done so far in the different scales, and then I'll just bring it together and conclude. So we began with the molecular atomistic scale level. So this work was mainly done by Intelia. So the main aim of this step was to get the vitrimer chemistries from the other partners in the project and use these chemistries and chemical formulations to extract the mechanical properties at the atomistic scale level. So this was done by using molecular dynamics and other techniques at the molecular level. So just as an example here, I have not included the results of the vitrimers yet, but I have just included an example thermoset that we studied. It's just a thermoset epoxy amine system. So these are the chemical formulations that we used. And on the bottom left, as you can see, we could extract the stress strain curves of these this polymer at different temperatures, at different strain rates. And as you can see on the bottom right, this is the modulus which is plotted against the strain rate. So all the points on the right side are obtained from the atomistic scale simulations that were performed. But as you can see, these results are obtained at very high strain rates. They are like around 10 power 6, 7, 10, 10 power 10 even. So we cannot perform the molecular scale simulations at the experimental strain rates, which are more like 10 power minus 2 to 10 power 2 or 10 power 4 at the maximum. So there is a discrepancy between what results we get from the atomistic scale and the properties that we need to perform FE analysis or to compare with experiments. So to bridge this gap in between the strain rates, we need to do something called property scaling. So here what it does is these methods take the properties which are obtained at very high strain rates and they are scaled down to experimental strain rates, lower strain rates. So I've just given a few examples here. I'm not going to go into the details right now, but some things that you might recognize are time temperature superposition, which can be used for simple materials, whereas for complicated materials like vitrimers especially, we need to choose models which can combine the whole behavior of the vitrimers. So especially when we see in vitrimers, there is cross-linking happening like normal thermosets, but also as mentioned earlier, there are some bond reactions happening at high temperatures. So at different temperature ranges, we have different properties, different behavior of the material, of the cross-linking, of the molecular cross-linking. So vitrimers will need complex models to be used to do the property scaling. But once this is done, we have got the properties of the vitrimers or polymers that we are analyzing from the molecular scale modeling and the scaling techniques. So now what we can do is we can apply these vitrimer properties together with fiber properties, the fiber geometry. So here I've shown UD volume element or a woven fabric or any other volume element, representative volume element that we can choose, together with the vitrimer properties that we have extracted and the fiber properties which are usually known from the data sheets and literature. So we take the properties of the matrix of the fiber, and what we can do is we can homogenize them to get the properties of a composite ply, which can be UD or bidirectional or any other orientation. So this is the first lowest step, the microscale modeling step done on the composite itself. And once we have these homogenized properties, ply properties, we can then take them to the mesoscale, which here, the mesoscale, by mesoscale, I mean the laminate level. So these are like laminate coupon or sample level, level structure. So we take the ply properties, which we have got earlier, and we take them to this multi-layered laminates, And then we can apply different orientations to them, different geometries, and we can replicate the experiments that we are performing, the experimental characterization that we are performing in the simulations. So here I've just shown an example of a dog bone shaped sample undergoing tension. So on the this is a complicated asymmetric layer laminate configuration. So you can see that the model provides information about the bending, which happens due to the asymmetry. We can get the stress distribution and all the other information that we need. So I have not shown this, but the last step in this would be to extend this to the part level analysis, which is currently ongoing in the project. So what we do here is we take all the information that we have got from the molecular scale, microscale, and mesoscale analysis, and we apply them to the entire wind turbine blade part, which is made out of the vitrimers that we are developing. So then we can predict the behavior of the wind turbine blade itself, subject to various loading like fatigue, like the complex loads that it undergoes during rotation, due to gravity, and we can include all these loads, and we can predict the behavior of the entire wind turbine blade part. So just in conclusion, what we are doing here, just to remind you again, is to create a multi-scale framework in which we can put in the vitrimer chemistry, any novel vitrimers that we are developing, and then we provide the processing parameters. We put the fiber properties, the geometries, various geometries at different scales. And once you have all this information, what this model can do is it can predict the vitrimer composite properties, the behavior of the composite on the macro scale. So this is quite a useful tool to have, and this is the work that is currently being done in the modeling side of EOLIAN. So finally concluding with a bit of learnings and the next work. So we have had a few challenges during this, obviously. So the property scaling process that I mentioned is quite manual. So for if you're working with different vitrimers, you might need to select different methods depending on the behavior of the vitrimers themselves. So again, to get the behavior, you might need to again perform experiments, which is something that we are trying to avoid by using the simulations. We are trying to minimize the experiments and get the properties from first principles itself. So the scaling process is quite manual now. So we are exploring other techniques as well to do this one faster. So this could include using some kind of physics-based models, material models, or it could even involve using surrogate models if we have the microscale, the molecular scale properties and microscale properties, we can use some surrogate model to bring them together and to bridge the gap between them. And a bit of future work as well. We are also developing a micro-mesoscale combined concurrent model, which will also enable the process to be less manual. It will automate the process. Right now, we are having to do the microscale model, create the material card, take it to the software for mesoscale modeling. If we can combine the process, it will surely speed up the entire methodology that we are doing. And also, as I said, we are extending it to part level analysis as well. So just generally, where can this framework be used for in the future beyond EOLIAN? It can be used for optimization of vitrimer or any polymer formulations, and it will aid in accelerating material discovery. It can also, once all these things are made automatic and it's made into a single framework, this model or framework can be used to create data sets for machine learning models for training them. Because as you know, these models require a lot of data, a large data set. So this framework can be used for that as well. And finally, it can be used to predict the properties of final parts, provided you know all the constituents. And it will minimize and it will help in pre-screening the polymers and vitrimers that are required, novel polymers and vitrimers that are being developed for certain part applications. Yep. So this is the work that we are doing right now in EOLIAN.
Okay. Thank you so much, Daniel. Very interesting insights. And we are going now from the UK to Greece. So let me see, Foteini. is here. And this is
Nice.
your presentation.
Yeah,
Yes.
thank you very much. Good morning, everyone. My name is Fotini Petrakli. I'm environmental engineer with a PhD in composite nanomaterials. Thank you very much for the opportunity to briefly introduce IRES, Innovation in Research and Engineering Solutions, and also our role in EOLIAN project. IRES in a nutshell. IRES is an R&D consulting company established in 2015. Our work focuses on three main pillars. The first is the sustainability and circularity. The second is the risk and nanosafety. And the third is the data science and material science and digitization. Through these areas, we support innovative materials, also products and processes from the early development within a project or a process up to validation, to the assessment, and finally to the implementation. Also in the field of sustainability, we provide life cycle assessment, life cycle costing, social life cycle assessment, also hotspot identification, eco-design recommendations, and we support environmental declaration and also labels. In the field of risk and safety, we work on occupational exposure assessment. We also provide VOC and airborne particle measurements. We provide hazard identification, FMEA, fault tree analysis, control banding, and also safe handling recommendation. Of course, depends on each project's needs. We also support projects with data-driven solutions and specific tools dedicated for this project. We develop machine learning algorithms, digital platforms. We provide process optimization and material data management and also data management plan. Within EOLIAN, we are leaders of Work Package 7, Sustainability Analysis and Risk Assessment. Here our main goal is to make sure that the new materials that will be developed within the project, as well as the manufacturing routes and the end-of-life strategies, are not only technically promising, but also safe, sustainable, economically viable, and also aligned with circular economy principles. The potential impact of this work is sufficient not only for the wind energy sector, but also for the composites sector. Nice. So in EOLIAN, IRES has a cross-cutting role actually. We connect, let's say, the technical development of new vitrimer-based composites with the real sustainability, safety, and cost performance. We assess the risk during manufacturing and also during handling. We evaluate the environmental impacts through life cycle assessment. We also examine the cost through the life cycle costing. And finally, we compare the new materials and processes with respective conventional alternatives, solutions that are currently used. Also, the goal is to support from the very beginning to the decision making and guide the project towards a safer and more circular and more scalable wind turbine blade technologies. Nice. The impact of IRES work, let's say, is important for both the wind energy and the composite sector. For wind energy, EOLIAN can help reduce the environmental burden of turbine blades and also improve end-of-life strategies, especially through recycling and reuse options. For the composite sector, the project can demonstrate that advanced vitrimer-based composites are not only high-performance materials, but also safer, more sustainable, and potentially more cost-effective alternatives in comparison with the conventional systems. So by providing measurable evidence through our assessments, risk assessment, LCA, LCC, and comparative impact assessment, we are trying to help translate innovation into credible solutions for industrial uptake. So actually, within EOLIAN project, IRES helps demonstrate the next generation wind turbine composites, that these materials can be safer, circular, sustainable, and finally real ready for the real world adaptation. These are all for me. Thank you for your attention.
Okay, so that was short and concise as well. Thank you to Boteini from Greece. And now we are going back to Spain, this time to Galicia. And that is Claudia Vasquez Sanz.
Hello, good
Claudia,
morning.
good morning. So this is your presentation. The stage is yours.
All right, thank you very much for the presentation. This is Claudia Vázquez from Spain, working in blade engineering, technical procurement in Norvento Tech and Power. And before heading towards our goal in the EOLIAN project, let me please briefly introduce my company and what we are doing. So, Norvento is a Spanish family-owned company which has been operating in the renewable sector for more than 40 years. We are present throughout the whole value chain of the renewables industry with three main business lines. The first of them is what we call the large generation, in which we develop and operate large-scale renewable power plants. We currently own more than 300 megawatts in wind. The second one is the energy solutions business line, in which we provide renewable energy solutions for self-consumption installations, always relying on renewable sources, such as solar power, wind energy, and biogas. And in the third place, we have Norvento Tech and Power, where we design, manufacture, and commercialize solutions for the renewable energy generation and storage. In this line, we in fact produce medium-sized wind turbines, for which we also manufacture the wind turbine blades. And in the EOLIAN project, Norvento's role is in fact to design, manufacture, and industrialize two wind turbine blades 12-meter prototypes, covering two different approaches. On the one hand, a traditional blade, which is going to be manufactured with a composite solution based on traditional materials, such as glass fibers and epoxy resins. And on the other hand, we have the recyclable blade, which is going to be produced using basalt fibers and the innovative vitrimer resin solution, which is being developed throughout the project. Both blades will account for the same external geometry, and they will be validated in terms of design and manufacturing throughout the whole project. The feedback that we will gain from this assessment will provide the company and also the stakeholders with the benefits and also the challenges that these new vitrimer resins may impose to the wind energy sector. Some of these challenges that we have already encountered throughout the design phase could be the differences in the material properties, since both plates will account for the same external geometry. It is very important to take into account the material properties in order to have a very similar structural efficiency and loads for the two composite solutions in the wind turbine. And additionally, in the manufacturing side, the main challenges come from the resin side. As mentioned by some of the members of the consortium in the previous presentations, the wind turbine blades are manufactured via resin vacuum infusion. So properties such as the viscosity, the glass transition temperature, and also the process temperatures play a key role in order to achieve good infusion and also process repeatability. So why is the EOLIAN project important for Norvento? Well, as a renewables company, Norvento has always been committed to sustainability and circularity. We are aware of how difficult it is to separate and to recycle the materials which are currently used for wind turbine blade manufacturing. In that sense, the EOLIAN project is looking for solutions to overcome these problems. And from Norvento, since R&D is a core part of our DNA, we find this project as the perfect opportunity to combine research with a step with moving forward towards sustainability. And in addition, the company finds this product as a very strategic product, not only for the wind turbine sector, but also for the company. And this is my presentation. Thank you very much for your attention. I will be happy to answer whichever question you may have.
Yeah, you've mentioned, Claudia, the wind blade production is done by resin vacuum infusion, correct?
Correct.
Okay, so that information, I will take that on later into the discussion, a technical one. So I will come back to you later on.
Thank you.
We will now continue with our last but not least guest, with Zeynep. And Zeynep, welcome from Istanbul. And this is your presentation, and I'm looking forward to hear from you.
Is it better right now?
Zeynep, yes, your voice is somehow delayed, but you keep talking. We have a separate recording, and we can always bring your presentation as a separate one. Just continue.
Okay, thank you. And then let me frame this an operator, our project. Today's plates are made from the composite materials, strong and light, and which let us build longer blades and capture more energy. But from where we sit, we have maybe we can say two headaches. They are hard to repair, and end of life, there's no easy recycling route. And as Europe and also and Turkey install more wind, that's a grow waste and the cost problem for our side. So EOLIAN attack us with the 4 ideas. So it helps us to the blades use vitrimers and new class of polymers that makes composite recyclable, and also vitrimers can be reshaped and can self-heal. And also there are sensors built into the blade monitor health and catch damage early. So also the bio-based and sustainable chemistry with every choice check through the life cycle and the cost analysis. So the project pros with the 12 meters demonstrated plate, so don't get lost in the chemistry for the owner. The headline is the plate that lasts longer, is easier to maintain, and can be recycled. So why it matter for us? Actually, I will start with the column that matters most to Zoran for us an operator, longer lasting, more reliable blades, lower O&M costs because we detect damage earlier, and the ability of the repair on the site rather than the replace. So when you run wind farms for 25 years, those 3 things are the difference between a good asset and a problem asset. This is exactly why an operator wants to be in the room while the blade is being designed. So for the composite and circularity, credibility of the recycling route for the blade waste, the reuse of the both resin and fibers, and less landfill. So a sector-wide problem that EOLIAN helps to solve. And the value chain is support the wind growth and the circular economy goals in the EU and also in Turkey. So builds the supply chain around these materials and sorting the path from the lab to the market, which precisely exploitation for the our leads. So this brings us is lifetime cost and the reliability. If EOLIAN delivers on those, and the operators will adopt it directly in the these new innovations. So actually, this is for all my side. Thank you for your listening. Also, thank you,
Zeynep.
Okay.
Thank you for your presentation then. Okay, then community, we are through our panelists, and I would like to call everyone on the screen right now. Please turn on your cameras. So Fortaini, Christina. So I do just a random row here. Okay, Andrea. Is everyone on now? Daniel, your camera, I can't see you. It's only white. Okay, I leave it out for now until I get a picture on yourself. Yeah, are you okay if I have some follow-up question in form of a discussion? Okay, so this discussion may be a bit upsetting to people in the wind industry. But I like to upset people because this way we can shake up a bit path that have been very, very strong. So, Claudia, you said the wind blade production is mostly resin vacuum infusion, right? And at the same time, Christina says we have to be careful about the same industrial processes. And my question to the panel, and please volunteer who has an opinion on this, is why are then industries so slow in adopting new, more modern processes?
Well, as working in the industry, what I would say is that you always have to take into account the complete value chain, not only the new materials, but also the cost of these materials, the cost of the new installations that you may need to produce in order to manufacture blades or whichever composite part with these new materials, certification, legal issues. So it's not only the way of introducing these new materials into our production, but also all the different factors that I already mentioned. The companies are very interested in trying new technologies, but it is also necessary to combine the introduction of these new materials and technologies with our current production processes and with our purchase orders for the clients.
Okay. And any more opinions on this? Now we got the manufacturer, of course. Yeah. Who else? Do you see resistance when you bring up new innovations like the bio-based polymers? Christina, you wanted to say something?
Yes, no, I want to say that I agree with Claudia because developing sustainable and recyclable materials is only the first step. Bringing them from the laboratory to the industrial scale applications requires collaboration about the entire value chain. And to transform, I understand that made some modifications, meet numerous technical and regulatory requirements. So it's difficult, and also it's a very manual, I think, procedure. So it requires more research and the participation of all the partners.
Mm-hmm. So then let me ask you, are you guys happy with the collaboration down there in the market, or do you feel any resistance towards the change? How is your experience?
Can I? Yeah, I don't want to be the defending lawyer for the industry, but on one end, in terms of technology, if vacuum infusion is the adopted technology, it means that most probably at the moment is the best technology. It's probably the role of whoever is doing the low TRL, in certain cases at least, if we want a quick uptake, and I think that circularity needs a quick uptake from the industry, to bring development in terms of material that allow to have a seamless transition to the traditional material, from the traditional material to the new material, if you get my point. Yes. Because there are already certain amount of hoops and hurdles that the industry needs to jump through to bring a new product to the market. Probably at this stage where we are, and it's a fairly emergency state with the environment, we need to be quick in proposing new material and propose new material that are quick to be uptaken by the industry. This is my feeling. That's why it's important to work on viscosity as similar as the viscosity of the resin that are already in use, TG, that are compatible with the requirements. I cannot, as a university, I cannot go and say, I throw at another technology. From now on, you're going to do the wind turbine blade at 15 meters. like Norviento or Tuvesas and tell them you're going to do a 115 meters blade with RTM because you need to use the vitrimer, and the vitrimer has a high viscosity, so you need to push it at massive pressure instead of drawing it with the vacuum. The challenge is to find a balance, and the interesting aspect of these projects, this Horizon project, is that you have the low TRL people like me and the very high TRL people like Claudia and Zineb in the same room, and they need to try to find a balance, a solution that is a balance, and a solution that works. This is the interesting aspects of this type of project.
Okay, then I push the ball to Zeynep. Claudia, I heard already. Zeynep, what do you think? Industrial processes that are established, change or not change?
Yeah, I think from our perspective, it's still trying to changing, but as Claudia and also Marcus said, we have a big, how could I say, sparkling for the industrial processes. So we will see. I can say that.
Okay, now the voice is gone, Zeynep. I'm not sure whether we can continue it. Okay, cool. Okay, then I would like to go from the technical away more to the commercial side. Andrea mentioned the cost on bio-based content is an issue. Andrea, can you explain what you mean by that?
Well, I mentioned two of the factors that are part of the challenging balance that Marco was also mentioning. So one is cost, and the other the bio-based content. Of course, we try to keep the bio-based content as high as possible. The good news from this side is that every year there is an increasing number of bio-based product for epoxies, also for other kind of polymer, but for epoxies that are available on the market at industrial scale. This means that cost is, let's say, is the same or is comparable, same order of magnitude to similar petro-based, fossil-based products. So this is a real help for people who is formulating in the lab or in the industry. So yeah, cost. We have some. I cannot, let's say, share here the cost figures that we have now in the project, also because they are not definitive. The real high cost part of the process is when at a low TRL, like at our scale, we make a synthesis and upscaling. So not with an industrial plant, not with a fully optimized process. In this case, the price per kilogram is of course high because it's main labor. It's not an efficient and fully optimized process. But yeah. I would say that overall, in the explorations of 3 families of formulation that we have made, and we are completing now in EOLIAN, we have been using a lot of commercial and bio-based products. So this is, in my opinion, a good sign for the composite industry and its sustainability.
Okay. Any more input from others towards the cost of the bio content?
If I may add, actually, it's well known that market is heavily driven by cost and revenues. And when it comes to adoption states, this is it is important to develop a cost-efficient composite materials. And all in all, sustainable innovation in general will only be adopted at scale if it makes sense for the industry. That means that not only lower environmental impacts, but also manageable costs in general, clear long-term value, and also support. It's very important to be supported from regulation and also from the market demand. So actually I agree with my colleagues.
Okay, wonderful. Marco, I would like to come back to you a final question before we close this round with a call to action or whatever you have prepared as your last statement. Marco, can people still join the EOLIAN? I'm seeing some interested people in the chat that are also in this industry, or how does that work in the future? Will there be other projects coming up?
So can they join the EOLIAN? Yes, we have an industrial advisory board, and if people are interested in taking part in the industrial advisory board, please contact me or ProPlast. As an active member, sadly not. At the moment, the project still has 1 year and a half to run. Correct me, guys, if I'm wrong. 2 years. Good that I have Andrea. That is more on the spot than we. We still have 2 years to go. Probably we will look at the end of the project if there is a scope for continuing with the second stage. Maybe some focus will need to shift, and some extra partner can join in. Can I just make a comment, because I was reading the message from Vitali?
Yes. Go ahead.
Yeah. So it's interesting. This is something that I always like to say about composite and composite recycling and circularity. We are now in a sort of point where we are carrying with us 25, 30 years of composite waste that was not designed to be recycled, and a lot of interesting solutions are coming up, like I see pyrolysis, for example, to deal with this waste with recycling. So maybe the image that we mentioned at the beginning of those buried wind turbine blade, those will become future mines to extract material that we can then reintroduce in circularity. Probably what we are doing here in EOLIAN is looking at the next 50 years. So design already with recycling and repair and circularity in mind. This is just what I wanted to say.
Okay, cool. So we've seen a few comments here. Dear community, thank you so much for everyone who tuned in. We have, unfortunately, a shy community, a lot of people watching us, but they are not commenting, they're not liking here. So if I may ask you, we are coming to the last round. Please make yourself visible, like you see here, Vitali, like Herbert, like Attila, they've wrote some comments. Don't be so shy. Write your comments here. How do you think was this information given by the panelists? We would like to hear from you guys. So anyway, so we are coming to our last round, and our last round is actually the call to action. So what should people now do after they have listened to you guys? Zeynep, let's try with you. I know your connection is not so stable today, but let's try. You need to unmute yourself first, of course.
Yes, sorry. Yeah, I have a problem with my connection and the computer. Sorry for that. Can you hear me, Leslie? I don't know.
Yes, I can hear you, yeah. So what is your call to action? What should people do now?
Okay. Okay, here's my main message, and it's concentrated from our position as an operator. Great matter is only matter if an operator will actually run them. And a brilliant recyclable blade that no owner is willing to put on turbine changes nothing. So what will it take for you and put recyclable and repairable blade on the real turbine? And it is operational data in a track record, the recognized standardization and the certification, or the maybe a commercial proof at scale, and a warranty you can trust. So, and to make the EOLIAN succeed, ask from the wider community, the collaboration, the standards and policy, the recognized recyclable blades, and the data and the demand, operational data plus can go to the market for the circular blades. So that's from my side.
Thank you. Forteine, you are next.
Okay. Actually, I want to underline again that sustainable innovation will only become an industry reality when environmental benefits are supported by a clear economic, also regulatory, and also strategic value. For example, if an innovative technology has lower environmental impacts but higher manufacturing cost, what would motivate an industry and the leaders and the decision makers to adopt this new technology? So I'd like to underline this point, which is, in my opinion, it's highly important.
Okay, thank you so much. Then Christina.
Well, I think that to make a circular wind turbine blade a reality, material developers, manufacturers, and end users need to work together to transform circularity from a concept to an industrial reality. And also regarding the implementation of electronics, the results obtained so far are very promising and demonstrate the potential of smart blades, but also additional studies of durability, scalability, and industrial integration will be essential before go to the commercial development.
Thank you, Christina. Then Julia.
Yeah, my point is to think about what can be the barrier for preventing vitrimers from becoming an industrial reality, and as we said, of course, an economical point of view for to become an industrial asset, and also, as we already mentioned, a technical point of view, so improving the formulation and carry on with the study on vitrimeric materials that are so promising. Thank you.
Okay, cool. Daniel, London calling.
Yeah, from my side, I would like to say that there are so many new numerical techniques and so many computing techniques that are being developed. And my call is for more research into how we can use those things to help in material discovery, to help in, as I said, the pre-screening, and to maybe reduce the experimental load. With so much of computing power, we can do so much more if both the sides collaborate, the numerical side and the material side, as demonstrated in this project as well. So yeah.
Okay, cool. Andrea.
Yes, a call to action could be think about in which application you would like to see vitrimers in action. I mean, can be in composites again, but outside the wind blade production, for example, with the different production process, different sizes. Could be, for example, in adhesives, which is adhesives are used a lot also in combination with composites, or in multi materials, composites plus aluminium. I suggest this call to action because we have explored tens and tens of formulations. Some of them are usable and we will use to make the the 14-meter wind turbine blade, but many others might be used in not usable for this application, but might be used outside. So there is room for sure for new uses and new developments.
Thank you, Marco.
Yeah, I would say that producing renewable energy is more than just generating clean electricity. We also need to think about what happens to the tool and the materials and the components through which we are producing this energy, and we need to think about their full life cycle. So the manufacturing, the maintenance, the repair, and the end of life. I think together with all the partner, Politecnico, but all the partners in EOLIAN, we are trying to develop material and approaches and technologies that can make wind turbine blade more durable, easier to repair, easy to recycle. But we need, and we are trying to move the solution from the little infusion plate that you saw in my presentation to a full-scale wind turbine blade. I think we need to connect with companies, researchers, policymakers, and everybody that who's interested in advancing more sustainable wind industry. But as Andrea was correctly saying, also the wider community of composites and maybe also of polymer user. So if people are working on materials manufacturing, health monitoring, recycling, wind farm operator, we are open to explore new ideas, share some challenges, and discuss any potential collaboration within EOLIAN and beyond. So please give us your input.
Thank you. Claudia, last but not least, your stance.
Yes. So my call for action for the audience will be for them to think which are currently the biggest barriers to promote the circular economy of wind turbine blades. I completely agree with the contributions of my colleagues, and I would like to highlight the importance of the synergy with material developers, R&D centers, universities, with the industry to develop these cost-effective solutions for the circular economy of wind turbine blades. And it's not only the cost that we should take into account, but the total cost of ownership. And there's still a lot of work to be done and many stakeholders involved in this process. And it's very important to account with the certification bodies and the policymakers support in this process.
Okay, wonderful. Thank you. All right, then we are through with the EOLIAN project. Let me take up this opportunity to thank the UCEA and the team for highlighting. This is the second project that we have spotlighted here on LinkedIn. The first was the Refresh project, and now this is the EOLIAN project. And I would like to bring to your attention, the UCEA has started a movement called ECCA, the European Circular Composites Alliance, that was launched at the last JEC in 2025. So it's now over 1 year and a couple of months old now. And yeah, you can sign it here. You see a QR code. Take it. If not, I will also tell you this is the ucia.eu/ECCA, eucia.eu/ECCA website. There you can sign for the ECCA and join our movement on circularity and sustainability in the composites industry that is organized with the UCEA, and UCEA has full support of the European Commission on this one. You can sign up for free. You are a free member with the ECCA, and the benefit is once you are an ECCA member, you are also entitled to get your seat at the next ECCA General Assembly, which will take place in December, and you will be then invited to be there. I was there on the first one. It was really cool to see all the people that are in the composites industry bringing a lot of effort and a lot of ideas, very creative, very influential people that are in the sustainability scene. So one more time, please take a picture of this ECHA QR code or just type in ucia.eu.ECHA. You can Google it also. I'm sure you will land there. So thank you for everyone for being part of our show. One more time, I will show everyone. And for my round here, before we say bye-bye, please make sure that your recording is at 100%, because this will be then transferred into a podcast later on. Thank you so much, everyone, and have a nice day.
Thank you.
Thank you.
Thank you.
Have a good one.
Thank you. Bye-bye.
How do we connect you with the stories within the composites and sustainable materials industry? We are on the ground to find the facts, and we examine big innovative ideas. To this end, we have launched the Composites Launch Engineering Talks. What is the Composites Launch Engineering Talks? That is abbreviated by CLET. The CLET is an online format where we are streaming live on LinkedIn, YouTube, and recording the panels for your favorite podcast station. Within the CLET, we are giving you a slot and your seat in a panel where we are talking about the entire value chain within the composites industry, from raw material to the end use. We have raw materials, substrates, and components supplying to OEMs covered in that panel discussion. From our online studios in Germany, we cover events and corporates from France, Italy, UK, Central Europe, and many more European regions. Stay informed, stay connected, stay inspired. Join us for creating sustainable value.
With Composites 360 on tour, Composites Lounge Engineering Talks, and Composites Lounge End User Panels, hosted by İlkay Özpizoğlu. Weekly on LinkedIn, YouTube, and your preferred podcasts.
The hard work of Composites teams should be shouted from the rooftops. We're on a mission to give your solutions better visibility and reach, to make them more widely known in the market and gain the appreciation they deserve. To make lightweight construction and specialized technologies available to end users, as well as attract projects, customers, and talent, join our Composites Lounge community. The Composites Lounge community is open to entrepreneurs, C-levels, specialists, and managers who want to create a better world with their innovative composites and play a key role in the success of their company. So if you're a hidden champion who isn't sure how to best promote your work, join a supportive and innovative community, which is focused on making composites achievements visible to end users. The Composites Lounge community celebrates and promotes the best innovations, lightweight construction technologies, and sustainable solutions in the automotive, aviation, renewable energy, oil and gas industries, and many more. Get involved at compositeslounge.com.
Composites Launch, İlkay Özpizoğlu, creating sustainable value today from Istanbul, where people see thought leaders bringing up the latest topics and trends, particularly in composites, industry, and advanced materials. We are seeing people working on sustainability and the future. To this end, welcome to our 2025 episodes of Composites 360 on tour. We bring you the brightest minds, influencers, and subject matter on your screen. With live panels at subject exhibitions, we are here to serve you with the latest content that is available in this industry. Whether it is aerospace, automotive, whether these are regional events like here in Istanbul, in Krakow, Poland, in Paris, France, or Germany, it could be also in Italy, We are here to cover those events in order to bring you the most pressing ideas and the most creative ideas to create sustainability and connect the global composites world. We invite you to join our Composites 360 on tour. I bring you the brightest, the best, and the farthest topics on LinkedIn.
İlkay Özküsoğlu, Composites 360 on tour with Composites Lounge weekly on LinkedIn, YouTube, and your preferred podcasts.